Hi everyone, welcome back to 2.7. What we do here in 2.7 is a transformation of functions. So it's a little different from things that we've done in the past. It's kind of like puzzling to an extent, puzzling in steps. But what we did at the very end of 2.6 was looked at, a nice library of graphs of different types of functions that we can see here in algebra. But what we're going to do now is learn to transform those graphs into other very complicated looking ones. So just as some basics, right, you could always use the table method for graphing, but this becomes really tedious or difficult the harder we get. So for example, if you wanted to graph absolute value of x minus 3, this isn't so bad. But the second you want to graph something like 2 times negative x minus 6 in absolute value plus 6, that's a lot harder. So transformations is a step-by-step method that helps us graph things based on a parent function. Basically, if we start with some function that we do know, we can do some sort of transformation to get to a function that we don't know. So here are some of the things that we looked at in 2.6, right? Quadratic squaring function x squared, cubic x cubed, absolute value of x, and root functions. So knowing what the graphs of x squared, x cubed, absolute value of x, and the nth root of x look like, we could take those that we do know and kind of mesh them to look into other ones, to look like other ones. All right, so the first type of shift we're going to talk about are rigid transformations. Rigid transformations are transformations that change the position of the graph, but not the shape. Okay, so vertical and horizontal shifts, most basic type of transformation. And you see here on this first slide, vertical shifts are going to be the most basic transformation. So vertical shifts for some function f of x, well, its transformed version, if you are vertically shifting it, would be f of x plus or minus k, right? So using g of x now instead of f of x, not to double dip. So f of x plus or minus k would be a vertically shifted function. So now the big thing here is that this plus or minus k is on the outside of the function. We're going to see some stuff where stuff happens on the inside, but for now, this plus or minus k is on the outside. If you have f of x plus k, so f of x plus k means you are taking your graph of f of x and shifting it up k units. And if we're shifting up k units, what we're doing is changing all the y values. So you would add k to all the y values to go from previous function to new function. For example, or not for example, as the opposite, if we have f of x minus k, well, f of x minus k is a shift down k units. Well, if you're shifting down, you're changing all the y values, you would subtract k units from all the y values. So this makes a lot of sense, I think, right? Plus k up, minus k down. Unfortunately, that nice intuition is not going to stick over the course of the section, but I think as a very basic type of transformation, it makes a lot of sense. Two very quick examples. X squared plus 2 would be the graph of x squared shifted up 2 units, or 2 units up, right? Either way. Absolute value of x minus 3 would be the graph of absolute value of x shifted down 3 units. Okay, so here's absolute value of x. Absolute value of x plus 2 would be take all the y values and shift them up 2 units, right? Shifting up. So 2, 2 would become 2, 4. 0, 0 would become 0, 2, right? Adding 2 to all the y values. Well, going to absolute value of x minus 3 instead, we're going to take all the y values and subtract 3 this time. So 2, 2 would become 2, negative 1. 0, 0 would become 0, negative 3. And now you see all three graphs, the original, vertically shifted up, vertically shifted down on one slide. Makes a lot of sense. Well, horizontal shifts are similar, but a little weird looking. So instead of plus or minus k on the outside, what we're going to have is minus plus on the inside. Now, that use of minus plus versus plus minus is very important, and you're about to see why. For f of x minus h on the inside, right? Again, big difference. Vertical shift plus or minus k was on the outside. This time minus plus is on the inside. If you have f of x minus h, where minus h is on the inside, this is a shift to the right h units. Okay, I am well aware that is backwards, that is uncomfortable. Vertical shifts are intuitive. They are as you'd expect. Plus K means up, minus K means down. However, horizontal shifts are counterintuitive. Minus H, you would really like to be to the left H units. That's not the case. It's backwards. So f of x shifted to the right H units, but if we're shifting to the right, that means we're taking all the x values and adding some value. So please be very careful the difference between vertical shifts and horizontal shifts. Vertical shifts, intuitive. Horizontal shifts, counterintuitive. Well, now that you know what f of x minus h is, f of x plus h would be a shift to the left h units, right? We like plus to mean right, but it doesn't here in horizontal shifts. In this case, we would subtract h from all the x values. Okay, two more quick examples. If we have x minus 4 squared, this is x minus 4 on the inside, but don't forget, minus 4 on the inside is a shift to the right 4 units. Okay, absolute value of x plus 6. We would really like plus 6 to mean to the right, but plus 6 means to the left 6 units. Okay. So here's x squared. If we want x minus 2 squared, well, minus 2 is a shift to the right 2 units. And if we're shifting to the right 2 units, we're taking all the x values and adding 2. So adding 2 versus subtracting 2, we see the difference, I think. All right. Well, if we add 2 to 2, 4, it becomes 4, 4. If we add 2 to 0, 0, it becomes 2, 0. And now you see how that graph is shifted to the right as opposed to the left. X plus 3 squared, this is a shift to the left 3 units. So 2, 4 would become negative 1, comma 4. 0, 0 would become negative 3, comma 0. So vertical, intuitive, horizontal, counterintuitive. Unfortunately, that's not the only time this is going to happen. Okay, reflections. So reflections are another type of rigid transformation because you're not changing the shape of the graph, you're still only changing its location. For reflections over the x-axis, its transformed version is negative f of x, specifically with that negative sign on the outside. Okay, so we say f of x is reflected over the x-axis, but what we're going to do is negate each y value. Okay, so what it means to negate something is to multiply all those values by -1. I want to be careful with my wording here. I can't say make that value negative, because if I say make that value negative, you're going to think in terms of like absolute value. Absolute value says make it positive. That's not what the case is. Negation says if it's positive, if some value is positive, its negated value is negative. If an original value is negative, its negated value is now positive, right? So very careful of that. In other words, just multiply all the y values by -1. That keeps you staying careful. So that's reflections over the x-axis. Reflections over the y-axis, well, instead of negative on the outside of our function, that negative would be on the inside of the function. So we say f of x reflected over the y-axis, but instead of negating the y values, we're instead going to negate the x values. So we're going to multiply all the x values by -1. So reflections don't really take us that long. Here's f of x equals x squared. But if I want negative x squared, negative on the outside, we're going to take all the y values and multiply them by -1. Well, 0, 0 won't change, but 2, 4 will become 2, -4. Okay, square root of x. Well, what if I want square root of negative x, specifically with this negative on the inside? Well, if that negative is on the inside, we're negating the x values, right? Negative on the outside here, negate the y values. Negative on the inside, negate the x values. So what we're going to do is make all the x values negative. Well, 0, 0 stays 0, 0, but 4, 2 becomes -4, 2. And it's actually kind of interesting because normally square roots need to be all positive, but if we're taking square root of a negative x, well, square root of negative 4 is square root of positive 4, which is 2. So that's reflections. Not really scary. Now the weird one, right? The least not least intuitive, I don't want to say, but the most involved type of transformation are stretches and compressions. We refer to these as non-rigid transformations because they can change the shape of the graph, right? Vertical shifts, horizontal shifts, reflections are just taking this graph in space and just kind of moving it around, but it doesn't change the shape. It just changes where it is. But stretches or compressions will change the composition of your graph. So let's start with vertical stretches or compressions. So g of x equals c times f of x. And I think you're already seeing the pattern of this c is on the outside. So kind of like x-axis reflections, if c is greater than 0, we're going to multiply all the y values by c. If c is negative, well, think about this. If this is negative 2 times f of x, this is like 2 times f of x, and then reflected because that negative is on the outside. So if your c is positive, it's one step. Multiply all your y values by c. But if c is negative, you're going to multiply all the y values by absolute value of c, and technically then do a reflection where you multiply all the y values by -1. If you're strictly going for the graph, you can multiply all the y values, in this case by -2 in one step, and that's okay. It'll have the same desired effect. However, what we're going to be interested in doing, at least in my classes watching, is understanding the order in which we do things. Well, the order in which we do things would be stretch or compression, multiplying all the y values by that constant, and then doing the reflection by -1. Now, different from class to class, that's how I prefer to teach it in my class. If the absolute value of c is bigger than 1, then what you do is stretch away from the x-axis. Your graph gets sharper, it grows quicker, so that's what it means to stretch away from the x-axis. Now, the phraseology here is going to get kind of complicated because right now we're doing vertical stretches or compressions, and then we're very shortly going to do horizontal stretches or compressions. But that's the idea here, that if your c is bigger than 1, even if it's negative, right? If this is 3, you take all the y values and multiply them by 3, it gets sharper. Even if you multiplied by -3, yeah, you would reflect, but your graph would still be sharper than the original. Likewise, if your constant is some fraction between between 0 and 1, like 1/2, well, then you're multiplying all the y values by 1/2, and if you're multiplying by 1/2, you're kind of dividing by 2. Well, in that case, you would get a lot closer to the x-axis. So if c is bigger than 1, you are stretching away from the x-axis, but vertical compression, you are going toward the x-axis. It gets closer, it doesn't grow as quick, it gets wider. That will be a compression. So here's absolute value of x. Let me move my picture. My picture still might be in the way. I really don't know how to get rid of having my picture appear twice. That's okay though. So if we wanted 2 absolute value of x, well, what we're going to do is take all the y values and multiply them by 2. So if we multiply all the y values by 2, this 1, 1 would become 1, 2. This 2, 2 would become 2, 4. And you see it got a little bit sharper. However, if I want 1/2 of x, well, this 2, 2 would become 2, 1, right? Take this y value multiplied by 1/2. 2, 2 becomes 2, 1. 4, 4 becomes 4, 2. So that would be a vertical compression because we are vertically compressing toward the x-axis. Here, we got away from the x-axis. Here, we went toward the x-axis. So away from the x-axis would be a stretch. Toward the x-axis would be a compression. Personally, if you're watching this and you're in my class, I'm not picky with how you word it. I'm more interested in the actual change itself. Okay, well, we had vertical stretches or compressions, and we have horizontal stretches or compressions, where we instead look at everything in the frame of reference from the y-axis. So instead of that C on the outside, we have a B on the inside. Okay, well, you're probably already starting to get the idea of how weird these things can be. Remember, for horizontal shifts, that -h meant add h, or to the right h plus h on the inside meant to the left h. So for this b on the inside, if your b is positive, you are going to divide all the x values by b, right? On the inside, we're affecting x now, but instead of multiplying, we are dividing. Constantly backwards when it comes to the inside. If your b is negative, well, this is like negative 2x on the inside. Well, negative 2x on the inside would be dividing by absolute value of b and then reflecting over the y-axis by multiplying the x values by -1. Very similar to what we were just dealing with in the last part, except now x values and division instead of multiplication. If your b is bigger than 1, then you compress toward the y-axis. And this is kind of hard to picture. Its meaning isn't perfect here in algebra. We need trigonometry to really see the difference here. But for now, yes, if your b is bigger than 1, you are compressing toward the y-axis. You're getting thinner. But if your b is a fraction between 0 and 1, then you would stretch away from the x-axis and you would get a wider version of the original graph. So kind of hard to tell, but here's x squared. And if I wanted 1/2 x squared, well, this b on the inside is between 0 and 1. So our graph is going to get wider. Well, so we divide all the x values by 1/2, which is really like multiplying all the x values by 1/2 to get the same, multiplying all the x values by 2 to get the same effect. So for example, this is x equals -1, but if we're dividing by 1/2, we're multiplying by 2. To get that same y equals 1, we now need -2. And you know what? Kind of notice this too, that this is 1/2 x squared. We could have also written this as 1/4 x squared without the parentheses, and then it would have been a vertical stretch or compression. So horizontal stretches or compressions, not super meaningful here in algebraic functions because it's a little harder to tell. But again, the effects are still the same. If we had 2x squared, we are taking all the x values and dividing them by 2. So instead of x equals -1 here, it would be x equals -1/2, right? Dividing by 2 to get that same y equals 1. But also notice this could have just been like y equals 4x squared, where it's a vertical stretch or compression. So horizontal stretches or compressions, kind of weird. You're probably not going to do a lot of them here in your algebra course, but definitely those things come in handy when it comes to pre-calculus. Okay, well, the order in which we do these things is as you see it on the screen. So the original graph, you start there. Horizontal stretches or compressions, you do that first. Then reflection over the y-axis if your b is negative. Then your horizontal shift. Then vertical stretch or compression. Then x-axis reflection if applicable, and vertical shift. And one thing I want you to know is, even though this is kind of daunting looking, right? There's a lot of information on this slide. Don't worry. The order in which we do these things is the order in which you would plug something in for x. So for example, let's take this really full version right here. If you were to plug some value in for x, well, maybe if you plugged in some value for x, as written here, you would subtract h, but then again, we could distribute this b, you would multiply by b, and then subtract h. Well, multiply by b, that's the first thing we did. And then subtracting h, oh, that's the next thing we did. Okay, well, then the next thing you would do, right? Okay, so you plug in some x, you multiply by b, you subtract h, which I know this isn't how this is written here, just showing you. But then what you would do after that is apply the function, right? Square root of squared. Then multiply it by c. Well, that was the next step right here. And then plus k. So order in which we do things is the order in which you apply things to x. The order in which we do these things in a nice simplified fashion is as follows. So our order, specifically for my class, right? You might in your classes be doing horizontal stretches or compressions, but like I said, they're kind of like vertical stretches or compressions in a lot of cases. Okay, so what we're going to do is start with our original graph and then do horizontal shifts. So in my case, I kind of cut out the horizontal shift. You can change you'd be able to change horizontal stretches or compressions into vertical stretches or compressions. But in odds are you're probably not going to get that deep. Horizontal shift, first thing we do. If we have f of x minus h, add h to all the x values, right? Horizontal shifts are backwards. If you have f of x plus h, we're going to subtract h from all the x values. Vertical stretch or compression, if we have c times f of x, multiply all the y values by absolute value of c. But if your c is negative, then do an x-axis reflection and multiply all the y values by -1. Vertical shift, very last thing we do. If we have f of x plus k, we're going to add k to all the y values. F of x minus k, subtract k from all the y values, right? Again, here now that they're side by side, notice the difference between horizontal shifts and vertical shifts. Okay, so just going back, here's all those parent functions that we had, but without further ado, let's do an example. Okay, so let's graph square root of x minus 2 plus 3. We want to start with square root of x. We know what square root of x looks like. We want to work our way to this. Okay, if you don't remember the order in which we do those transformations, that's okay. The order in which we do transformations is the order in which you would do something to x when you plug it in. So for example, we plug in some x, and what's the first thing that happens to it? Well, it's not plus 3. You wouldn't take the square root of it yet. The first thing you would do is subtract 2. That's the first thing you would do to x. Now, what does x minus 2 on the inside mean? X minus 2 on the inside is a horizontal shift. And if we have minus 2, that's a horizontal shift to the right 2 units. Okay, so you plug in some x, you subtract 2, you take the square root of it, and the last thing you would do is plus 3. Plus 3 on the outside is a vertical shift up 3 units. Now, depending on your class, depending on who's teaching it, again, this one is very centric to my classes. I think I teach this kind of weird, but I hope this is still helping you. But this is one way you can write it. This is the very formal mathematical way of writing transformations. But also, if you just want to describe what's happening, you can also use it in words. So shift right 2, add 2 to the x values. Shift up 3, add 3 to all the y values. Exactly the same as what's happening in the coordinate parts, but for the description parts, you're literally describing what's happening, just not giving the function part. So in my class, if you're watching, I don't care about either. It's one way or the other. So here's square root of x. First thing we said was to shift right 2 units and then up 3. So there is our transformed version of the graph, and we didn't need to do any table of values, I should say. No table of values. All we had to do is take something we already knew, shift it to the right 2, shift it up 3, and that's how transformations work. Okay, let's do another one. We have negative absolute value of x minus 2 plus 3. Parent function here, where are we going to start? Absolute value of x. Okay, now the order in which we do things is the order in which we apply things to x. So x minus 2 on the inside, right? You plug in some x and you would subtract 2 first. Well, we just saw on the previous page that subtracting 2 is a horizontal shift to the right 2 units. All right, so you have some x, you subtract 2, you take the absolute value of it, then do you do negative or plus 3? Well, you do the multiply by a negative sign. Well, negative on the outside is a reflection over the x-axis, but if we're reflecting over the x-axis, we are multiplying all the y values by -1. We are negating all the y values. Well, last but not least, all right, you plug in an x, you subtract 2, you take the absolute value, you multiply by -1, and then you add 3 last. Okay, and then if we're adding 3 on the outside, this is a vertical shift up 3 units. And again, this is the nice mathy way of writing it, but if you wanted to give a description of what's happening, here you go. All right, here's absolute value of x. we had a horizontal shift to the right 2 units, we had an x-axis reflection, and then we went up 3. So there's our nice finally transformed version. No table of values at all. Okay, let's do another one. 3 square root of x plus 1 minus 2. What we're going to do is start with square root of x, because that's our parent function, right? We see the square root here. First thing we would do is the plus 1, but plus 1 on the inside means shift to the left 1 unit. Then would we multiply by 3 or subtract 2? We would multiply by 3 first. And if we're multiplying by 3 on the outside, what we're doing is taking all the y values, multiplying by 3. And last but not least, minus 2, that's the only thing we were missing. Minus 2 on the outside means down 2 units. There it is in words. Okay, first thing was to the left 1 unit, multiply by 3, and down 2 units. And there's our nice transformed version. So these are transformations. I think we got 1 or 2 more examples. Negative 2, x minus 1 squared plus 3. Okay, well, first thing you would do when you plug in an x would be the minus 1. Start with x squared, and then we do x minus 1 squared. Minus 1 on the inside is a horizontal shift to the right 1 unit. Then we would have negative 2 on the outside, but technically the order in which you would do this would be the 2 first. So we would multiply all the y values by 2, and then you would make it negative in terms of 2 separate steps. Here is the vertical stretch or compression. Here is the reflection if we're describing what's happening. So you could, if you're not looking to describe what's happening, you could do these 2 into 1 step. But again, you'll see on the next slide in terms of words how their descriptions are very different. So if you were to combine this into 1 step using like the mathy steps, it would just be x comma negative 2 times y. Last but not least, we got the plus 3 on the outside. That's a shift up 3 units. In words, here now maybe you see why we need to do it in 2 steps. Vertical stretch by a factor of 2, reflect over the x-axis. It's hard to combine those 2 into 1 step when we're using, words to describe it. All right, first thing was to the right 1, then stretch by 2, reflect over the x-axis, and then up 3. And there's our nice final version of this transformed graph. So that's transformations. Transformations kind of weird, kind of quirky if you're not careful, but if you stick to doing it as a step-by-step method, it's not as bad as it seems. So with that said, thank you so much for watching, and I will see you in 2.8. Yeah, bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska-Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.